Hey everybody, this is Mr. Caldwell here to talk to you about bond polarity. And bond polarity is really sort of the next piece of our puzzle of learning as it relates to covalent molecular compounds. And in order to understand bond polarity, understand what poles are. There's a north pole and a south pole. If you're talking about magnets, there's a north and a south, all right? And so in atoms, you've got positive charges and negative charges, all right? So they can also be like poles on a bond. And so in order to understand this concept of bond polarity, we really do need to get at another idea, which is electronegativity, all right? And this has nothing to do with positive and negative charge or being someone who's down on everything, no negativity. It's the measure of the ability of an atom to attract bonding electrons to itself. All right, and we'll use this idea of electronegativity to determine whether or not a bond is going to be a nonpolar or polar covalent bond, or possibly even an ionic bond. Now let's go back and review a couple of things from basically periodic trends. So if you think back to earlier in the year in chemistry, we should remember that as we go down any group, all right, we're getting more and more electron layers. We're getting more and more orbitals, so the atoms are getting bigger and bigger and bigger. And so the valence electrons are they're held on to less and less tightly. All right. And remember the trend as we move across a group. All right. We remember that as we move across a group, we're not so much talking about adding electron levels. Right? We're talking about increasing the strength of the nucleus. Lithium over here has just 3 protons, whereas neon over here has 10 protons. Those 3 protons in lithium don't hold on to their electrons anywhere near as tightly as those 10 protons do for the neon. So we already have in our mind some ideas about who's going to hold on to electrons more tightly. All right, neon, because it's very, very small, right, and it has a relatively strong nucleus, going to do a really good job of holding on to electrons. But all of these elements, the noble gases, not so reactive, so we probably won't worry too much about the noble gases. So let's focus our attention over here on the halogens. Of the halogens, fluorine going to have a relatively strong nucleus and be very, very small. So fluorine is going to be very good at attracting electrons to itself. As we sort of think about the opposite, who's going to be not very good at attracting electrons? Well, francium. Francium, even though it has a ton of protons in the nucleus, right, is a big honkin' atom. All right, and so even though the nucleus has 87 protons, the electrons not held onto super tightly, which explains why it's so reactive, and those electrons are very far away. So what we're talking about here in discussing bond polarity is in essence a tug of war. Right? Some atoms are going to pull more strongly on bonding electrons than others. So maybe we think about it like this. I've got something that's really good at holding on to electrons and pulling them towards it, like the fluorine. And then I've got something that's going to be not as good, because let's face it, I don't care how many people you got, this looks like a really strong horse. So let's kind of see what this ends up looking like, because it's just kind of funny. So look at fluorine go. Fluorine is taking those electrons, and this is not even a fair match, is it? My goodness gracious. Oh, goodness. Well, those people just got shown how it was done. So let's talk about this. Electronegativity. All right? Electronegativity is the ability to hold on to attract bonding electrons to a given atom. There's a table of electronegativity, and this might look like the electronegativity table that your teacher gives to you to use. And so let's look at sort of this tug of war is going to fall into roughly 3 categories. So let's first focus on elements that have roughly the same strength, okay? And we've been talking about covalent bonds. We've been talking about molecular compounds, and those are going to be between the nonmetals and other nonmetals. So we'll focus on that first. And the first example that I have is if I look at fluorine bonded to fluorine. All right, we got a nice single bond there. We could draw a Lewis dot structure. We could even determine the shape of it based on our previous lessons. But today we're focusing on the electronegativity difference. So I look at this table and I see that the electronegativity of fluorine is the highest value of any of the elements on this table. So fluorine, when it's bonded to another fluorine, there is no difference, all right? There's no difference in electronegativity, all right? So if there's no difference in electronegativity, they're going to hold on to those shared electrons that are bonding the two fluorines to one another. They're going to hold on to those electrons equally, right? So it is a very balanced sharing arrangement. And that's going to have a name that we're going to talk about in the next portion of our lesson. So small electronegativity differences, and all I'm doing is simple math. I'm just taking the electronegativity of one, the electronegativity of the other, and subtracting them. Now that's if they are the exact same thing. What if I have two elements that are slightly different, but still, right, not very different at all? If I do that math, right, if I go ahead and I drag this out of the way, and for some reason, there it goes, it wasn't moving. I take the electronegativity of sulfur and I subtract the electronegativity of selenium, and I see that, man, there is no difference at all. That would be like a tug of war with two teams very equally matched. No one's really going to win, all right? So the shared electrons in that covalent bond, very equally shared, all right? And that's what I want to highlight over here. So when we have a roughly equal strength, right, we are similar in electronegativity. That's my shortened version of electronegativity, E-negativity. Couldn't fit it in there. All right, so what would this look like when I have roughly equal sharing? All right, here's another example. Carbon and hydrogen, pretty small electronegativity difference. And the electrons that are shared in that bond are going to be roughly equally shared. So you see a kind of a representation of that. There's roughly the same amount of shading around the H as there is around the C. But there's not always equal shading, all right? Sometimes you get a little bit less equal. So now let's look at a situation where there's still sharing. It's still going to be a non-metal and a non-metal, all right? So we're still talking about covalent bonds, but it's not as equal. So let's go find sulfur and chlorine. So we look at the electronegativity values there. I've got 3.16 for the chlorine, and I've got 2.58 for the sulfur, and that's a difference of 0.58. A little bit larger than what we were talking about in the previous couple of examples. All right, so here, maybe one team is a little bit better at pulling on the rope than the other. In this case, the chlorine is going to attract the bonded electrons a little bit more tightly to itself. Another example here is nitrogen and fluorine. And so if I wanted to get an indication of the relative strengths of these two, I would look at the values, and then I'm going to see what the difference is. The difference is 0.94, and because fluorine has the higher electronegativity, it's going to draw those bonded electrons, the single bond, well, in this case, it depends on what the bond is, but it's going to draw those shared electrons in the covalent bond a little bit towards the fluorine side of the bond, all right? So when we have one atom that's a little bit stronger than the other, all right, we have kind of a medium difference in electronegativity. Well, what might that look like in a picture? Here's an example of some unequal sharing, all right? We've got some oxygen and some hydrogen, and they're still nonmetals. So we're still talking about a covalent bond, but we have a little bit more of an electronegativity difference. In this case, you've got a difference of about 1.24. So you just look at the table, you subtract the values, you've got your electronegativity difference. Now, what happens when so far we've been talking about nonmetals and nonmetals. Well, in the previous unit, back before winter break, we were looking at the metals reacting with the nonmetals, and we called those ionic bonds. So let's look at some examples of how electronegativity difference might look like for a metal paired up with a nonmetal. So I've got oxygen at 3.44, bonded to a calcium at 1.00. That's 2.44. That's way bigger than the differences for either of the other sets of examples we've looked at. So we're now in a situation where this isn't even a fair game. This is like the horse pulling on all of those people. The people were never going to win, all right? In this case, oxygen is just so good at pulling electrons towards it, it really just takes the electrons from the calcium, right? There's no sharing here. This is a straight up stealing relationship. And so if I lose electrons, I become a positive ion, and if I gain electrons, I become a negative ion. So when the electronegativity difference is really big, we're not talking about covalent bonds anymore, right? We're talking about an ionic bond. So depending on electronegativity difference, we can determine whether we have a covalent bond and its polarity is maybe there's not so much difference, right? Maybe there's a little bit of difference. And then if they're so far apart that it doesn't even become a covalent bond anymore. Now we're talking about an ionic bond. And the next video that you're going to look at gives these three distinct regions, these three distinct sets of values, different names here. So big differences in electronegativity. That's what's happening when we see a metal paired up with a non-metal. Okay, you guys have a great day. Bye-bye.